Hello everyone, welcome to Computer Science and IT Gate Coaching. Don't forget to subscribe my channel and press the bell icon to get the instant notification of my free lecture. In the previous lecture, we have seen omega, theta, big O, big omega, omega, small omega, big O, small o, omega and small omega. This four we have seen in the previous lecture. Now in this lecture, we are going to see big theta. Okay, we are going to see big theta. To give heading big theta. So write if we have a function, if we have a function f which is growing with respect to with respect to n, then we should then we should then we should find out we should find we should both the upper bound both the upper bound and lower bound by a function just by varying the c. C is the constant. Okay, it's a value of constant. So here I am saying that big theta, if we have a function f which is growing with respect to n, it is growing, then we should find out both upper bound and lower bound by a function. So same one function I will use to find out the upper bound and lower bound, that function only, just by varying the c, means the constant. Okay, just by varying the constant we are going to get the both upper bound as well as the lower bound. If you are done with the writing, then please let me know. So here it will grow with time, here it will grow with n, the input. Okay, so if your function, like if it is growing like this, it is growing like this, it is growing like this is your function fn. Now takes, this is your c2 gn. Okay, now this is your c1 gn. Yeah, good evening Abhishek. Now with the function gn only, you are bounding the fn. Here it's the upper bound, here it's the lower bound. Okay, and the input, this is the n0. After this n naught, this c1 gn is always smaller and c2 gn is always greater. Both we have to see. Okay, so this is called as, for this condition, if for a function f you are finding some gn such that if you vary the constant, then that function should be smaller than c2 gn and that fn will be greater than c1 gn. Okay, c1 gn, then you can say that fn is equal to theta of g. So both lower bound and upper bound, just by varying the c1 and c2 are two constant, c1 c2 are two constant, C1 comma C2 is greater than equal to 1. Okay. So mathematically now I will write. So now write mathematically. Fn is equal to theta of Gn. Fn is equal to theta of Gn if C1 Gn is smaller than equal to Fn is smaller than equal to C2, C1 C2 greater than equal to 1, n is greater than equal to n naught, and n naught is greater than equal to. And give a note and write after that small theta does not exist. So we are not having any concept called as small theta. Small theta doesn't exist. So only small omega and small o exist. Okay. Yeah, correct, Chandra. Gn are both the same function with different constant. Then we can say that it is a theta. Fine. Are you done with the writing? Can I go to the next slide now? So now go to the next slide. Now take an example. The same example the previous day we have seen, the previous lecture. If Fn is equal to 3n plus 2 and Gn is equal to 2, sorry, n. Gn is equal to n. So that we have seen that Fn was both big O of Gn and it was also Fn was also of omega of Gn. That we have seen in the previous lecture. How? So you write down 3n plus 2 was smaller than 4n. For in previous lecture we have seen for n naught greater than equal to 2 and n is greater than equal to n naught and c is equal to 4 and 3n plus 2 was greater than equal to n for c for n naught is greater than equal to 1. For n naught greater than equal to 1, n greater than equal to n naught and c equal to. So for if just by varying c I am saying that 3n plus 2 is smaller than 4n and sometimes 3n plus 2 is greater than n. Okay, so now we can say that Fn is theta of Gn. Am I clear? So Fn is bounded by, please write it fast. So Fn is bounded by Gn both in upper bound as well as lower bound. That's why Fn is equal to theta of n. So that's why Fn is equal to theta of n. And because of this, sometime theta is also called as asymptotic notation. Okay, sometimes it is even called as asymptotic notation. Asymptotic equal, not notation, asymptotic equal. Okay, so because of that only, sometimes theta is also called as asymptotic equal. That is important because sometimes they will ask you what is the asymptotic equal of that. So it means they are asking about theta. Okay, so give a note, and this is the trick that you are going to use. Always it is going to satisfy if the leading term, the leading term the leading term is going to n as in 3n plus 2, then it is theta n, so if the leading term is going to n as in 3n plus 2, then it is theta n. So whatever will be the leading term in a equation, in a function, that is going to be the theta. So here the leading term is n, that is going to be the theta. And similarly, for 3n square plus n plus 1, the leading term is n square, that is going to be theta n square. Whatever will be the leading term, that is going to become the theta of that. So always the leading term is going to theta. Always the leading term is going to be your theta. Whatever will be the leading term, here n square is the leading term, is going to be the theta. So now in GATE exam, just by seeing the equation, because this n square is going to determine the major part of that function, because this is going to give the bigger value. Okay, that's why we are taking the leading term. Am I clear? Practical significant. Practical significance of big O, omega and theta. Practical significance. This is the practical significance of. So how, when we are going to use big O? Okay, so I have told you that whenever we are going to do some programming, then we also want to know the worst case time complexity. So big O is going to give the worst case, omega is going to give the, tell me what omega is going to give the best case, and theta is going to give you the average case. Okay, so right, this is the practical significance. So big O is going to say worst case time, or the upper bound. Omega is going to say the best case, theta is going to say the average case. Okay, if you're done with the writing, just let me know. I will go to the next slide and I will take one example, and with this example we will try to find the best case, average case, and the worst case. Now take an example. If an array is having this 5, 7, 1, 2, 4, 10, 20 and 11. Okay, this is your array. Now let us assume I am asking you to search an element x in this array. Let us assume your when your element is 5, when x is 5, then you are going to get in the beginning when you will search, just like assume that in every cell you are going, just like linear search, in every cell you are going and searching whether it is equal to 5. Yeah, you got. So best case you are going to get 1, and worst case you will get at the last So worst case will be whatever will be the length, and average case will be the n by 2. In middle you can get, and that is going to be the leading term you are going to take, that is going to be n. So in this way we are going to find the omega. So best case is the best case when the first element, the element which you are searching is in the beginning. Worst case when the element which you are searching is in the last, and average case when it is in the middle. Understood? So your asymptotic notation is complete now.